The corollary on the function of bounded variations. If f is of bounded variation on closed interval ab, then f dash exists for almost all x in the closed interval ab. Almost for all x in this closed interval ab, f dash exists. So before starting with the proof, we need to read this remark that is very important. Let f be an increasing real valued function on closed interval ab, then f is differentiable almost everywhere. If I'm having a function f which is increasing and also real valued function on closed interval ab, then f is differentiable almost everywhere. So I'm going to use this remark at the end of the proof. And the proof is almost the same as that of the previous one. So let's start with the proof. It is given that f is a bounded variation on closed interval ab. So let f is of bounded variation on closed interval ab. And we need to define the subdivision of closed interval ab. So let a is equal to x0 less than x1 less than x2 up to so on xn, that is taken to be equal to b. This be any subdivision of closed interval ab. Right? And then we need to define the small p, that is the summation on f of xi minus f of xi minus 1, and because it is your positive variation, so I'm writing here positive sign. Then n is equal to the summation I going from 1 to k f of xi minus f of xi minus 1, because it is your negative variation, so I'm writing minus sign over here. Then the total variation is equal to the sum of p and n. That is equal to taking the summation on the modulus of f of xi minus f of xi minus 1. And then we need to define this capital P, that is the positive variation over the closed interval AB. So this is equal to the supremum of small p and can be written as capital P. Then capital N is the negative variation on closed interval a to b and is taken to be the supremum of small n and is written as capital N. Similarly, the total variation over closed interval from a to b, that is the supremum of small t, can be written as capital T, denoted as capital T. Then the first part is, we know that from here the negative variation is always less than equal to the total variation, and also the positive variation is always less than equal to the total variation. And we also know that, please remember this always, the difference of p and n is equal to fb minus fa. It is very important. Please note this remark always. And now in the first step, I am taking this small p alone on the left hand side. In the second step, I will take small n to be on the left hand side. So here I am taking first small p on the left hand side. So this is equal to f of b minus f of a plus n. And because this small n is less than equal to capital N. Why? Because capital N is what? It is the supremum of small n. So small n is always less than equal to capital N. Right? So let's use this in the next step. So I can write this p to be less than equal to fb minus fa plus capital N. I hope it is very clear. Okay. Now taking the supremum over all the possible subdivisions of closed interval AB. Over all possible subdivisions. So we get, when we take the supremum, this small p is changed into capital P. Yes. Less than equal to fb minus fa plus capital N. Now since this capital N is always less than equal to capital T and total variation is finite always, so now I can take this capital N to the other side for this. So therefore p minus n is less than equal to f of b minus f of a. You have to mention this for this step. Please mark this as 1. Now moving on to the second part. Now this time I'm going to take n alone on the left hand side. So this is equal to, when taking minus common, you will be getting p minus f of b plus f of a. We can also write this as p plus f of a minus f of b. This is your small p. Okay. Now this small p is always less than equal to capital P. Why? Because capital P is what? It is a supremum of small p. So taking this on the next step, this n is now less than equal to capital P plus f of a minus f of b. And now taking the supremum over all the possible subdivisions of closed interval AB. And when taking the supremum, this small n will be changed into capital N. Very fine. Less than equal to capital P plus f of a minus f of b. Again, since this p is always less than equal to t and t is finite, therefore I can take this p now to the left hand side. So we have n minus p less than equal to f of a minus f of b. Or we can also write this as, if I take minus common, this is p minus n, sign will be changed, and this is f of b minus f of a. And when cancelling the negative sign, so that is p minus n greater than equal to f of b minus f of a. Marking this as 2. What is 1? P minus n is less than equal to fb minus fa. And in the second part we have shown p minus n is greater than equal to fb minus fa. So from 1 and 2 can I write, we get the sign of equality now, that p minus n is equal to f of b minus f of a. Or we can also write this as fb minus fa is equal to, I'm writing the notation, the capital P, that is the positive variation over closed interval a to b, minus the negative variation over closed interval a to b. Now if I consider any x belonging to this closed interval ab, I can write this equation for the closed interval ax. Can I write? So for this I write, just replace this b with x, which means this x can be equal to b, or it can be less than equal to b, or strictly less than b, right? So this is fx minus fa equals to the positive variation over the closed interval from a to x minus the negative variation over the closed interval from a to x. So let me consider this p from a to x to be my gx and n from a to x to be hx. So let's consider gx to be the positive variation from a to x, and considering hx to be the negative variation from a to x. Then g and x are monotonically increasing functions, because the positive variations and the negative variations, these are always monotonically increasing. So writing this, then gx and hx are monotone increasing functions. I have already explained this in the previous video in details. Now since this PAX is less than equal to the total variation from a to x, yes, and this further can be less than equal to the total variation from the closed interval a to b, right? And this is, I know that this is finite, always finite. And similarly, this negative variation from a to x, this is less than equal to t a to x and is less than equal to t from a to b and is finite. So both these are finite, which means PAX is what? Gx. NAX is what? Hx. If PAX and NAX are finite, that means h and gx are finite. And if hx and gx are finite, which means these are real valued functions. They give finite values, right? So writing here, therefore, gx and hx are real valued functions. Okay, very fine. Now since fx minus fa is pax minus nax, right? Pax is what? It is gx. Minus nax is what? It is hx. So we have f of x minus f of a to be this. I need this fx alone. So this f of x is equal to g of x minus h of x plus f of a. Right? So this is equal to g of x minus h of x. If I take minus outside, I get hx minus f of a. Now since this is also increasing and this is also increasing, right? So since gx and hx minus fa is increasing, so we have found that this function fx is a difference of two increasing functions. And now let's move on to that remark which we have read. The remark is, let f be an increasing real valued function on closed interval ab, then f is differentiable almost everywhere. We have shown that this f is because it is difference of two increasing functions. These two are increasing and these two are also real valued functions. Yes, we have also shown that gx and hx are real valued functions. If these two are increasing and real valued functions and this f is equal to the difference of these two, then f itself is also increasing and real valued function on closed interval ab. Then from here I can say now that f is differentiable almost everywhere because I have shown that this f is an increasing real valued function. Yes? So which means f is now differentiable almost everywhere. So now using this remark, since gx and hx minus fa is increasing real valued function. Now since gx and hx minus fa is increasing, which means these are differentiable almost everywhere using the remark. So therefore gx and hx are differentiable almost everywhere. AE means almost everywhere. Almost everywhere. So thus, because f is a difference of these two functions which are differentiable almost everywhere, from here we say that f equal to g minus h minus f of a is differentiable almost everywhere. Hence, we further write that f dash x exists for almost all x belonging to the closed interval ab. Right? So here the proof ends. We have shown that f dash x exists for almost all x belonging to closed interval ab for f to be the bounded variation on closed interval ab. Alright, thank you, stay blessed.